Okay, let's unpack this. When you look at the towering skyscrapers, the intricate bridges, or even the cozy home you're in right now, have you ever truly considered the astonishing complexity that goes into building them? It's far more than just bricks and mortar.
Oh, absolutely.
Way more. Today, we're diving deep into the world of construction, from the ground up, to peel back the layers and uncover the surprising insights and crucial elements that truly define this foundational industry.
Yeah.
Our mission for this deep dive is to extract those essential nuggets of knowledge that will make you genuinely well-informed, allowing you to see the built world with new eyes.
That's precisely it. This deep dive is your shortcut, not just to general knowledge, but to a nuanced understanding of an industry that shapes every aspect of our lives, often in ways we take for granted.
Right. We just sort of live in it.
Exactly. We're going beyond mere definitions to explore the art, the science, and the intricate business mechanics that underpin every single project. Our sources provide a comprehensive view, from fundamental principles and complex processes to the fascinating materials and specialized terminology. It's going to be a thorough yet highly accessible journey into how our physical world comes to be.
Let's start right at the beginning then, with the very definition of construction. It's a word we use constantly, but its etymology offers a powerful insight into its enduring nature.
It really does.
It stems from the Latin word constructio, which breaks down into com, meaning together, and struer, meaning to pile up.
Together, pile up.
When you consider the sheer complexity of today's mega projects, isn't it remarkable how that ancient root still perfectly captures the essence of bringing elements together to form something greater?
It's kind of amazing, actually. It still holds.
It's truly one of humanity's most complex industries, encompassing an incredible blend of artistic vision, scientific precision, and keen business acumen.
It absolutely is. Expanding on that, construction is essentially the process wherein a design is translated into the real world, into tangible matter.
Right, from paper to reality.
Exactly. But it's not just about stacking, it's about the precise manner in which materials are ordered, assembled, and united into a whole.
Ah, okay, there's an order to it.
A critical order. This holistic approach is what transforms raw components into intricate objects, complex systems, or even entire organizations. It involves everything from the initial, absolutely critical site preparation.
Can't build without prepping the ground.
Nope. Then through the meticulous erection of the structure, the assembly of countless components, and finally, all the detailed finishing operations.
It's a long chain.
A very long chain. And this brings us directly to the concept of a project within this context. A temporary endeavor undertaken to create a unique product, service, or result.
Okay, temporary and unique. Those seem key.
They are the distinguishing characteristics here. Temporary meaning it has a defined start and a definite end. It doesn't go on forever.
Unlike some projects feel like they do.
True. And unique. Even if it's a standard building type, like an office block, each project is unique to its specific site, its design variations, and its particular requirements.
So location, maybe different floor plans.
Exactly. Which means a project manager never truly builds the exact same thing twice. There's always something different.
So if every construction endeavor is a temporary, unique project, what are the absolute non-negotiable foundations, the unshakable pillars that every single project, regardless of its size, relies upon?
The fundamentals.
We often refer to these as the four corners, or the key players that must be considered right at the outset. But how do these pillars, each with its own demands, interact and often create tension throughout a project's life cycle?
That's where the real challenge and the real art of project management lies. These four pillars dictate the entire scope and feasibility. They're always in a kind of tension.
Okay, so what are they?
First, you have the site. This is the geographical location or venue. It's foundational because it dictates the physical canvas.
Where you're actually building.
Right. But it also introduces critical variables like soil conditions, local regulations, access for materials and labor, and even environmental factors that can significantly impact the build.
So the site itself presents challenges.
Always. Second is the program. This defines the determined needs of the users, what the building is for, how it will function, who will use it.
The why behind the build.
Precisely. It's the blueprint of purpose. Getting the program wrong here means the entire building might not serve its intended function, no matter how perfectly constructed it looks.
A beautiful failure, potentially.
Could be. Third, the schedule. This outlines the sequence, timing, and duration of all the works required to complete the project.
The timeline, how long it all takes.
But this isn't just a calendar, it's a meticulously planned progression of tasks, where delays in one area can create cascading failures across the entire project. It's interconnected.
The domino effect.
Exactly. And finally, the budget. This is the financial allocation. It's the economic framework that dictates what can be built, to what quality, and how. Money talks.
Always does.
The tension often arises because clients, understandably, want a perfect program on an aggressive schedule in a prime site.
But within a limited budget.
You got it. Balancing these four is the constant tightrope walk of construction. It's about trade-offs, priorities, and smart management.
Here's where it gets really interesting, because once you have those four corners established, you move into the truly intricate and sequential nature of actually bringing a building to life.
Right, the roadmap.
The project schedule isn't just a static list of things to do, it's the dynamic roadmap from an initial concept to a completed structure. What are some of the less obvious complexities or critical junctures within this timeline that often surprise people?
Oh, there are plenty. It's a multi-stage orchestration where every phase builds on the last, and neglecting one can have exponential consequences down the line. It's not linear, it's layered.
Okay, walk us through it.
Let's do it. It all begins with the initial phase. This includes things like contract negotiations, where the foundational agreements are set, pretty crucial.
Setting the rules of the game.
Exactly. But what's often underestimated is the programming pre-design stage. This is where those user needs are solidified. And believe it or not, the vast majority of project costs are implicitly decided right here.
Wow, really? That early on?
Absolutely. Getting this wrong, misunderstanding needs or overlooking future requirements can lead to exponential budget overruns later, even if the design itself looks perfect on paper. An interior survey might also happen here, critical for renovations to understand the existing conditions you're working with.
So measure twice, cut once, applies to planning too.
Very much so. Once that groundwork is solid, we transition to the design and estimation phases, after the presentation of the design concept and its approval.
Getting the green light on the vision.
Yep. We move into schematic design. This is still high level, kind of like sketches, but it's complemented by a conceptual price estimate.
A first look at the potential cost.
Right. And the critical part here is the subsequent review and approval of the budget estimate. This isn't just a rubber stamp, it's a crucial checkpoint where financial reality meets design aspiration.
The reality check moment.
Definitely. If the budget isn't approved here, you go back to the drawing board. No point designing something you can't afford to build.
Makes sense.
The next significant phase is design development. Here, the concept is refined with much more detail, followed by another essential review and approval. This leads to the preparation of the comprehensive construction documents.
The actual blueprints and specs.
Exactly. These documents, the blueprints and specifications, are the Bible for the contractors. Any ambiguity or error here can lead to costly RFIs. We'll get to those and change orders later. Precision here saves money later.
Got it. Document everything clearly.
With documentation complete, the project goes into bidding and award. This involves bids and negotiations and the formal award contract.
The competition phase.
It's a competitive landscape where contractors vie for the project, and the selection often comes down to balancing cost, schedule, and demonstrated capability. Who can do it best, fastest, for the right price?
A tricky balance for the owner.
Always. Before any major physical construction, there's pre-construction mobilization. The absolutely vital step here is acquisition of permits.
The bureaucracy.
Yep. Without these, you literally cannot legally break ground, and bureaucratic delays here can be a major source of frustration and cost. Patience is required.
I can imagine.
Once permits are secured, mobilization of site begins setting up the construction area, bringing in equipment, establishing temporary facilities like site offices.
Getting ready to actually build.
Finally. Then we enter execution and completion. Construction administration is the day-to-day oversight, managing subcontractors, quality control, problem solving on the ground. It's constant management.
Keeping all the plates spinning.
You bet. The final stage, installation of furnishing, makes the space ready for use, putting in the desks, chairs, whatever is needed.
The finishing touches.
Each phase demands meticulous planning, coordination, and the ability to adapt, because the real world rarely follows a perfect plan. Unexpected things happen.
Always.
A continuous flow of information and the willingness to proactively manage risks are key to avoiding delays and cost overruns. Communication is paramount.
That's a truly comprehensive timeline, and it makes you realize just how many moving parts there are, each with its own financial implications.
Every step costs something.
All those stages, all those materials, all that expertise, it all translates into a budget.
So what does this all mean for the financial side of things? Let's break down where the money actually goes.
Yeah, let's follow the money.
Because understanding the components of a construction budget is absolutely crucial for comprehending project viability and successful management. It's more than just a single number, it's a strategic allocation.
You're absolutely right. The budget is a carefully structured allocation of funds across various categories, and misunderstanding them can be costly. The first and most straightforward category are hard costs.
Hard costs sounds pretty direct. It mostly is, yeah. These are the direct costs explicitly for the physical construction of the building itself. Think of anything that becomes a tangible part of the structure.
So the actual stuff you build with, like steel, concrete.
Exactly. All the raw materials, steel, concrete, wood, wiring, plumbing, everything. Then there's the labor, the wages paid to all the skilled and unskilled workers directly on site.
The people doing the actual building.
Yep, from masons to electricians. And finally, equipment costs, covering everything from renting large machinery like excavators and cranes to purchasing the smaller tools used daily.
With tools of the trade.
Right. They're called hard because they're physically tangible and typically easier to quantify and track. You can see where the money went.
Makes sense. Tangible items, tangible costs.
Next, we have general conditions. Now, these are a bit different. These are the general contractor's non-trade costs.
Non-trade, meaning?
Meaning they don't become part of the physical building itself, but they are absolutely essential for the project to run smoothly. Think of them as the operational overheads for the construction site.
Ah, the costs of running the site, not just building the thing.
Precisely. Imagine temporary utilities like power and water, essential for running equipment and providing basic amenities. You need lights, you need water.
Sure.
There's crucial project supervision salaries for site managers and foremen who ensure safety, efficiency, and adherence to plans. Someone has to be in charge.
Management on site.
Yep. Other examples include dumping services for waste removal. Construction creates a lot of waste. Printing for all the blueprints and documents, trailer rental for temporary offices, sometimes called temp cell or temporary facilities, and various project management and administrative costs.
So all the background stuff that makes the work possible.
Exactly. A common misconception is to underestimate these, but cutting corners here often leads to significant inefficiencies, safety issues, and even major delays down the line. It can actually end up costing more if you skimp here.
Penny wise, pound foolish.
That's the idea. Then there are soft costs. Despite their name, these are anything but insignificant.
Soft costs implies less tangible.
That's right. Soft costs cover design and other professional services not directly tied to the physical building, but indispensable for its legality, design integrity, and overall success.
Okay, like what?
This includes substantial architectural and engineering costs for all the design work, structural calculations, system planning, the brains behind the operation, essentially.
The design fees.
Yes. Insurance and bonds are critical here, too. Specifically, Air-I contractors all risk insurance. This provides comprehensive coverage for potential damages during construction, a vital safety net if something goes wrong.
Protection against accidents or disasters.
Definitely needed. You'll also find legal and accounting fees for navigating contracts and financial compliance. Lawyers and accountants get their piece.
Naturally.
Design consultancy fees for specialized advice, perhaps from a lighting expert, an acoustics consultant, sustainability consultant, anyone bringing specific expertise.
Specialized knowledge.
And crucially, project management fees for the overarching coordination and oversight, ensuring everything stays on track from a higher level. Trying to skimp on soft costs upfront often results in costly redesigns, legal battles, or even structural failures later. Investing here prevents problems.
So soft doesn't mean unimportant.
Not at all. It just means not physically part of the building fabric. Finally, we have permits and fees and contingencies.
Yep.
Permits and fees are the crucial legal authorizations required before construction can even commence. We mentioned permits earlier. You need that official permission slip. These fees are typically calculated based on the project's scope and size, ensuring compliance with local regulations.
You got to pay the government to let you build.
Pretty much.
Yeah.
And then there's contingency. This is absolutely vital. It reflects the harsh reality that Expect the unexpected is basically the first rule of
That's
construction.
the O fund.
Exactly.
Yeah.
It's money set aside for unforeseen circumstances that are almost guaranteed to arise. Something always pops up. Our sources detail different types of contingencies, each serving a specific strategic purpose. First, design contingency. This is for design changes that may be needed after the initial design is set. Maybe a new building code is introduced mid-project, or the client realizes they need something different functionally, forcing a design tweak.
So changes to the plan itself.
Yep. Then there's construction contingency. This covers unforeseen work or materials necessary to simply complete the construction as planned. For example, you start digging the foundation and hit unexpected solid rock that needs blasting, or there's a sudden shortage of a specific material driving up its price.
Problems during the actual build.
Right. There's also owner contingency. This
Yeah.
is a separate fund allocated by the owner, their money set aside, for possible additional work or materials they might decide on mid-project. Maybe they want to upgrade the finishes or add a feature not originally budgeted,
Owner changes their mind, basically.
or just wants something extra. And finally, escalation. This is money needed specifically to account for significant increases in construction costs, especially for materials, due to unpredictable market fluctuations. We've seen a lot of that recently with supply chain issues.
Inflation protection, essentially.
Sort of, yeah. For construction costs specifically, these layers of contingency aren't just slush funds, they're essential strategic tools. They provide vital flexibility and risk mitigation in what is always a dynamic and unpredictable environment. You need these buffers.
Every specialized field has its own lexicon, its own language, and construction is definitely different.
Oh, for sure. It's full of jargon.
It's more than just jargon, though. It's a language that defines the mechanisms of control, communication, and risk mitigation within a project. Mastering these terms is like getting a backstage pass,
Yeah, it lets you understand what's really going on.
allowing you to understand the subtle nuances and critical distinctions that truly drive a build.
Exactly. Understanding this specialized vocabulary is absolutely key to navigating the industry's operations and avoiding costly misunderstandings. You need to speak the language.
So let's break down some of the must-know terms.
When a project is out for bids, you might encounter an addendum. This is written information that clarifies or modifies the bidding documents issued during the bidding process before the contract is signed.
So an update before everyone submits their price.
Right. It ensures all contractors are bidding on the same updated information, promotes fairness, prevents disputes later.
Makes sense.
Similarly, an alternate refers to additional design or material options added to the construction documents specifically to obtain multiple cost estimates for those options.
Like price it with option A and option B.
Exactly. This allows the owner flexibility. They can see how add alternatives, adding optional features, or deduct alternates, removing certain things to reduce cost, would impact the overall budget before committing.
Gives them choices.
A bid is simply a contractor's offer or proposed price for doing the work. Pretty straightforward. But the real game changer in a project's life often is a change order.
Ah, the infamous change order.
Indeed. This is a formal, written document, and crucially, it must be signed by both the owner and the contractor. It authorizes a change in the work, or an adjustment to the contract sum, or even the project timeline. Sometimes architects or engineers might sign too if they're authorized.
So it formally changes the agreement.
That's the key. It's the legal mechanism that formally modifies the contract after it's been signed. Mismanaging even one change order can lead to significant cost overruns and delays. It's often cited as a major reason projects go over budget.
Got to track those carefully.
Absolutely. For communication during the build, an RFI, or request for information, is vital. It's a written request from the contractor to the owner or designer asking for clarification of the contract documents.
So something's unclear on the drawings.
Precisely. Imagine a detail on a drawing is ambiguous. An RFI is the formal way to get that clarity before you build it wrong. It saves time, money, and prevents errors. Very important communication tool.
Proactive problem solving.
Then there's an RFP, or request for proposal. This is a written request asking for an estimate or cost proposal, often sent from a general contractor to potential subcontractors or suppliers for specific parts of the work.
Asking for prices for specific jobs.
Exactly. On the regulatory side, we mentioned the building permit. That's the official green light written authorization from the appropriate government authority permitting construction according to the approved plans. No permit, no legal work.
the official permission slip.
Right. And at the very end of the project, a certificate of occupancy, or C of O, is issued by the local government. This states the building meets health and safety codes and can be legally occupied.
The final stamp of approval saying it's safe to use.
That's it. You can't legally move people in without it.
Crucial document.
Documentation also includes as-built drawings, sometimes called record drawings. These are the original contract drawings that have been marked up during construction to reflect any changes made along the way. They show what was actually built, not just what was planned.
So an accurate map of the final building.
Exactly. Their importance cannot be overstated for future renovations, maintenance, or troubleshooting. If you need to fix something later, you need to know where the pipes really are, not just where they were supposed to be.
Makes perfect sense.
Shop drawings are another key type. These are incredibly detailed drawings prepared by the contractor, or, more often, a subcontractor or supplier. They illustrate precisely how specific parts of the work will be fabricated, assembled, or installed. Think detailed plans for structural steel connections or custom cabinetry. The designer has to review and approve these.
Getting into the real nitty-gritty details.
Absolutely necessary for complex components. And the regulatory body overseeing much of this is the Office of the Building Official, OBO. This is the government agency responsible for implementing building codes, issuing those permits, and inspecting buildings to ensure compliance. They're the enforcement arm.
The building police, essentially.
In a way, yes. In terms of roles and oversight, construction management is the overall organization and direction of the labor force, materials, and equipment to build the project as designed by the architect and engineers. It's the orchestration of all those moving parts on site.
Making sure it all comes together correctly.
Right. A consultant is an individual or firm hired by the owner or designer for specialized advice in their area of expertise: acoustics, lighting, landscaping, structural engineering, you name it.
Bringing in the specialist.
And a field order is different from a change order. It's a written order for a clarification or a minor change in the construction work that does not involve any adjustment to the terms of the contract, meaning no change in cost or time.
So a quick clarification on the fly.
Sort of. It's for minor things to keep work moving without the formality and contractual implications of a full change order. Think of it as a minor course correction.
Got it.
Finally, for the non-fixed elements, we have FF&E. This stands for furniture, fixtures, and equipment.
Stuff you put in the building but isn't part of it.
Exactly. These are the movable items that don't require permanent connection to the building's structure or utilities: desks, chairs, computers, lamps, artwork, even some appliances. This distinction is important because FF&E are often procured and budgeted separately from the core construction contract, giving flexibility in interior design and fit-out phases.
Separating the building from its contents.
Pretty much sums it up.
Okay, so you can have the most brilliant plans, a perfectly managed budget, all the right contracts signed.
What ducks in a row?
But without the right tools, it all stays on paper, right? Let's talk about the muscle and precision of the build, the physical instruments that transform raw materials into finished structures. How have tools, over time, truly transformed what's possible in construction?
Oh, it's an incredible evolution of capability. I mean, fundamentally, the transformation of raw materials into functional structures relies entirely on a vast array of specialized tools and equipment. Each step up represents a huge leap in power and efficiency.
Where do we start? The basics.
Yeah, let's start with hand tools. These are the tools powered solely by human strength. They are the foundational instruments, really representing the direct connection between human skill and the material being worked.
Like hammers and saws.
Exactly. Think of the universal tape measure for precision, the chalk line for laying out perfect straight lines over distances, the ubiquitous claw hammer for driving and removing fasteners, various screwdrivers for different types of screws, and handsaws for cutting wood. Simple tools like chisels for shaping wood or stone, and a level bar to ensure things are perfectly horizontal or vertical.
The absolute essentials.
Right. While simple, these tools require immense skill and precision to use effectively, and they remain absolutely indispensable for countless tasks that demand a human touch, nuance, and control.
Can't automate everything.
Not yet, anyway. Next, we moved into power tools. These employ power from external sources: electricity, batteries, compressed air, revolutionizing speed and efficiency.
Making things faster and easier.
Massively. This category includes essential items like power drills for rapid hole creation, various power saws, circular saws, jigsaws, Reciprocating saws for quick and precise cuts through materials like wood or metal, power hammers like demolition hammers, and power nailers and staplers for incredibly fast fastening, driving hundreds of nails in the time it took to hammer a few by hand. Even welding machines fall into this category, using electrical power to join metal.
A huge leap in productivity.
Absolutely. The introduction of power tools didn't just speed things up. It fundamentally transformed safety protocols on construction sites too, requiring new training and precautions. More power means more potential danger if not handled correctly.
Good point. What's next up the scale?
Moving up, we have specialized equipment. These are more complex tools and machines designed for particular jobs, often requiring more than one operator or specialized training to use safely and effectively.
Bigger, more specialized machines.
Right. Examples include things like conveyors for efficiently moving large volumes of materials like gravel or sand across a site. Surveying equipment, like theodolites or total stations, used by surveyors for highly precise layout and elevation measurements, ensuring the building is exactly where it's supposed to be. Water and concrete pumps for transferring fluids or concrete over distances or up heights, and various mixers, most notably concrete mixers, that ensure materials are properly combined on-site for optimal strength.
Machines designed for specific, large-scale tasks.
Exactly. This category reflects the growing specialization and mechanization of tasks within the construction process.
And then the really big stuff.
Finally, at the pinnacle of power and scale, we have heavy equipment. This category encompasses incredibly large, complex, and powerful machines designed for monumental tasks that human power or smaller machines simply cannot handle. This is the earth-moving, heavy-lifting machinery.
The giants of the construction site.
You got it. This includes bulldozers for massive earth-moving operations, pushing vast quantities of soil or clearing debris, towering cranes, mobile cranes, tower cranes capable of lifting immense loads like steel beams or precast concrete panels to great heights, literally shaping city skylines. Excavators with their powerful arms and buckets for digging foundations, trenches, and moving large amounts of earth. And specialized things like highway equipment for road construction, pavers, rollers, graders.
The machines that make mega projects possible.
Absolutely. The advent of heavy equipment fundamentally reshaped not just construction sites, but entire urban landscapes, making projects of unprecedented scale and speed achievable.
It's truly incredible to visualize this progression from the humble hammer that fits in your hand to those colossal cranes that dominate city skylines.
It really is.
Each one, regardless of its size, plays a vital and specific role in transforming raw materials into finished structures, bringing designs to life with precision and power. Now, for something a bit different, a truly fascinating detour that highlights the global nature of construction, but also the deep local wisdom embedded in its practice.
This is interesting stuff.
While many construction terms are universal, reflecting shared principles of engineering, every culture often develops its own specialized vocabulary, right?
Definitely. Based on local materials, traditions, or just common usage.
So let's explore a few vernacular Tagalog terms used in buildings, specifically in the Philippines. This offers a unique glimpse into how specific building components are conceptualized and discussed on the ground there.
Yeah.
This isn't just about translation. It's about seeing how language itself can reflect practical, ingrained understanding and even cultural nuances.
This segment truly fascinates me, as it shows how knowledge adapts and localizes. These terms aren't just direct equivalents often, they sometimes carry a unique practical or historical resonance within the Filipino construction context. Language reflects practice.
Okay, give us some examples.
All right, let's look at some building parts first. You have post for a column, the vertical support. And hallage is often used for a wall, though historically it could also mean a main house post. So fundamental structural elements.
Post and hallage, you got it.
For beams and supports, you have gilion for a girder, a main beam, sileras for a joist, smaller beam supporting floors or ceilings, and biga simply for a beam.
Different types of horizontal support.
Exactly. Sahig or suelo means flooring. Sipo is a girt, a horizontal framing member in walls.
Okay.
For roof framing, barriculan is the bottom chord of a truss, riostra is a purlin supporting the roof sheeting, and sinepa is the fascia board at the roof edge.
Specific terms for roof parts.
Very specific. For walls, tabike is siding, external. Inside the wall frame, pillaret is a vertical stud, and pabalagbag is a horizontal stud, or blocking.
Vertical and horizontal framing pieces.
Yep. Around windows, pasamano is the windowsill, sombrero, literally hat, is the window head, and hamba is the window jamb or door jamb.
Makes sense. Sill, head, jam.
For trusses again, cinturon is the collar plate. Stairs have great terms. Jardinera is an open stringer where you see the steps from the side, while madre de escalera is a closed stringer.
Madre, mother of the staircase.
Literally. It suggests that nurturing backbone idea, right? Batang is the tread, what you step on, and gabe is the handrail.
Nice visual names.
Moldura is molding. Saib is the eave, roof overhang. Balada is a projection or overhang. Baluncas means the general framework of the structure.
Framework. Baluncas.
Canal can mean gutter, or sometimes a groove. Alilad is the downspout or conductor.
Water management terms.
Fasteners and connections. Planchuela is a WI or wrought iron strap. Pierno is a bolt. Plancha, interestingly, means scaffolding.
Plancha for scaffolding, okay.
Finishing work. Costurada is a plastered course. Paletada is stucco or plaster finish. Rebocada is the scratch coat, the first rough layer of plaster. Piqueta refers to pickwork on masonry, roughening it for the next coat. Muñeca is a varnish finish, often referring to French polish.
Layers of finishing.
Technical details. Viento means spacing or a gap. Largamasa is a rough concrete slab. Assentada means alignment. Hulog is the plumb line you use to check verticality.
Alignment and verticality.
Critical.
Tiles and doors. Baldosa is a cement tile. Batidora is a door fillet. De bandeja means a paneled door.
Okay.
Material properties and fills. Haspe refers to good grain and wood. Escombro is earth fill. Lastillas is masonry fill.
Different fill materials.
Metalwork. Hinang means solder. Estaño could refer to a nickelite bar or tin plating. Suban or subihal means temper and metalwork.
Working with metal.
Bracing and tools. Pedigallo, literally rooster's foot, is a diagonal brace. Consul is a nail setter. Palea is a wiring knob for old-style electrical wiring. Espelon is a specific type of cabinet hinge.
Pitagallo for a brace. Love it. Isn't that great? And there are specific terms for hand tools, too.
Oh yeah, like what?
Cabra is a pry bar. Metro or metrasan refers to both a folding ruler and tape measure. A modern one might be digital gnaw laser for a digital ruler laser.
Metro makes sense.
Escuala is a framing square. Label, nibel, or libel is a level. Pitik is the chalk line or chalk box.
Pitik for the snap line.
Yep. Martillo is the general term for hammers, including the claw hammer. A bigger one is a masso or sledgehammer. Distornillador is a screwdriver, and tornillo is the screw itself.
Martillo mosso. Okay.
Ligari is a handsaw. A hacksaw for metal is ligari bakal, iron saw. Pipe is a wood chisel. Cincel is a cold chisel for masonry or metal. We mentioned punzel for a nail set.
Different saws and chisels.
Liabi is a pipe wrench. Kutsara, literally spoon, is a brick or masonry trowel. A finishing trowel is a rodella or float. A large one for concrete floors is a mahabang rodella or bull float.
Kutsara for a trowel.
Yeah. Riveter is a blind riveter, and pala is a shovel.
Wow. That's quite a list.
It is, and it just shows how deeply embedded these practices are in the local language.
That's a truly fascinating segment. It highlights how construction is not just a universal technical practice, but one that is deeply woven into the fabric of local language and culture.
Exactly.
These vernacular terms offer a glimpse into local practices and the historical continuity of building knowledge across cultures, showing how people have adapted and named the components of their built world over generations, often with a subtle cultural meaning embedded within the word itself, like madre.
It adds a whole other layer to understanding the build.
Okay, so now that we've covered the how and what of construction, the processes, the finances, the tools, even the unique terminology, let's explore the what is it itself, the magnificent end product, the anatomy of a building.
Right, the thing itself.
We'll look at it from its deepest roots, where it meets the earth, to its highest reaches, where it meets the sky.
A building is truly far more than just walls and a roof. Our sources define it quite precisely as a relatively permanent enclosed structure constructed over a plot of land for habitable use.
Okay, permanent and habitable. Key words.
Absolutely. Permanent differentiates it from a temporary project structure like scaffolding or a site office. And habitable means it's designed for human occupation or use, whether it's living, working, storing things. This fundamental purpose guides every design and construction decision, demanding rigorous safety and functionality.
It has to work for people.
It has to work, and it has to be safe. To understand its anatomy, we can break a building down into its major structural divisions. The foundation is the critical structural part that transfers the building's entire weight onto the ground below, anchoring it securely. Can't overstate its importance.
The base, it all rests on.
Then, below ground level, you might have the substructure. This is any habitable or usable part of the building located there. Think basements, cellars, underground parking levels.
Anything below grade.
Right. And then everything that extends above ground level is the superstructure. This is what we typically see and interact with: the walls, floors, roof.
The visible part.
Mostly. Within these major divisions, a building is comprised of numerous building components, which we can categorize by their function to make sense of it all.
Okay, break it down for us.
First, you have structural components. This obviously includes the foundation, but also the floor systems, the horizontal surfaces we stand on, which also play a crucial role in transferring loads sideways to beams and columns,
The skeleton, basically.
the skeleton and the platforms. Then for the envelope and dividers, you have the wall systems that enclose the space, providing shelter and defining rooms. And within those walls, you have doors and windows that provide access, light, and ventilation.
The skin and the openings.
Good way to put it. Shelter systems are crucial for protection from the elements. This includes moisture and thermal protection, things like insulation, vapor barriers, waterproofing membranes, weather stripping, and of course the roof system itself, the primary overhead protection.
Keeping the weather out and the comfort in.
Exactly. Moving inside, interiors encompass the finish work, all the visible surfaces like drywall, paint, flooring, ceilings, trim the aesthetics. It also includes special construction, which might be unique, bespoke elements like a built-in fireplace or specialized lab equipment fixtures.
The look and feel, plus unique bits.
And finally, running throughout the building are the vital building systems. These are like the arteries, veins, and nerves. Mechanical systems include HVAC, heating, ventilation, and air conditioning. Plumbing systems handle water supply and waste removal. And electrical systems provide power and lighting.
The guts of the building.
You got it. All these systems must work in concert, integrated into the structure, for a building to be functional, comfortable, and safe. It's a complex machine.
Definitely sounds like it. What about the core frame? How does that work?
Right, the typical structural frame. Specific elements are designed purely to carry and transfer loads efficiently. A load, first off, is simply the weight or pressure from gravity, wind, people, snow, borne by the structure.
The forces acting on it.
Yes. The floor is the base surface of a room we walk on. Supporting that floor, you often have joists. These are horizontal structural members, usually smaller beams spanning open spaces, often running between larger beams. They collect the load from the floor decking and transfer it sideways to the beams.
Joists hold up the floor.
Correct. Then you have girders or beams. These are larger, rigid structural members designed to carry and transfer those transverse loads acting perpendicular to their length to supporting elements like columns or walls. They essentially collect loads from joists or directly from the floor slab and pass them along.
Beams collect load from joists.
Often, yes. Supporting the beams, you have columns or posts. These are rigid, usually slender vertical members designed primarily to support axial compressive loads pushing straight down their axis. They carry the weight vertically down towards the foundation.
Columns hold up the beams.
Generally speaking, yes. And at the bottom, connecting the column to the foundation and the ground, you have the footing. This is the part of the foundation bearing directly on the soil, spread out to distribute the load safely.
Footing spreads the load onto the ground.
Precisely. And the site, of course, is the ground itself, the earth upon which the entire foundation rests and relies for support. It's a whole system transferring load from the roof all the way down into the earth.
A continuous path for the weight.
That's the goal of structural design.
That's an excellent breakdown of the building's skeleton and vital organs. But how do buildings, these massive structures, stay standing against the relentless pull of gravity and the powerful, often unseen forces of nature like wind or earthquakes?
Ah, the forces.
How do engineers design for the unseen battles a building fights throughout its lifespan? This leads us back to the fundamental concept of loads, right? These are critical to structural integrity.
It's all about anticipating and resisting forces. You can't see the forces, but they are absolutely real, and engineers meticulously calculate and account for various types of loads a building must withstand to ensure its safety and stability over decades. It's a core part of engineering.
So what kinds of loads are we talking about?
First, there's the dead load. This is probably the easiest to understand. These are fixed, static loads made up of the building's own permanent structure. Its skin, the cladding or exterior walls, fixed equipment, and other permanently attached elements.
The building's own weight, basically.
Exactly. Think of the unchanging weight of the concrete walls, the roof tiles, the structural steel frame, the glass, the built-in cabinetry. This weight is constant and doesn't move throughout the building's life. Engineers can calculate this pretty accurately.
Oh, okay. Dead load. Fixed.
Then we have the live load. These are moving or transient loads. They are not permanent fixtures. This includes the weight of occupants moving around inside, the furniture that can be rearranged, stored materials, and also environmental factors like accumulated rain, snow, and ice on the roof.
Things that come and go or move around.
Precisely. These loads can change in magnitude and position over time. So engineers have to design for the maximum potential live load anticipated for a given space, according to building codes, like how many people might be in a classroom or office at once.
Designing for the worst case reasonable scenario.
Essentially, yes. Then you have wind load. This refers to the pressure exerted by wind on the building's surfaces. This primarily creates lateral loads, meaning horizontal forces that try to push the building sideways.
Wind pushing on the sides.
Right. But wind can also create uplift forces on roofs, especially sloped ones, trying to pull them upwards, or significant downward pressure. Designing for wind is particularly challenging for tall, slender structures or those in hurricane-prone areas, as these forces can be immense, dynamic, and change direction rapidly.
So, resisting being pushed over or having the roof torn off?
Crude, but accurate. Finally, we have a category sometimes called other load dynamic forces. This catches several important types. It includes sudden forces like impact loads, for example, a vehicle hitting a ground floor column, or heavy equipment dropped inside. It also includes shock waves and vibrations from external sources like nearby heavy traffic, trains, or industrial machinery.
Sudden or vibrating forces.
And crucially, this category also includes seismic loads, which are the forces generated by earthquakes. These are highly complex, dynamic loads that shake the ground, and therefore the building, in multiple directions. Designing for seismic loads requires advanced structural analysis to ensure the building can deform and absorb energy without collapsing during an earthquake.
Making sure it can withstand shaking.
Exactly. Engineers use sophisticated computer models these days to simulate and calculate how the structure will respond to all these varied forces: dead, live, wind, seismic, impact, ensuring the building remains safe and stable throughout its intended lifespan, even under extreme conditions. It's a huge responsibility.
The stronger the foundation, the stronger the building, as the old saying goes. We hear it all the time. But what exactly is a foundation, beyond just being the lowest part? How does it work to manage all those complex loads you just described?
Yeah, it's more than just concrete in the ground.
It feels like foundations are where the building's dialogue with the earth really begins.
That's a great way to put it. The foundation is truly the unsung hero, the critical interface between the massive, concentrated weight of the structure and the variable, often yielding ground beneath it.
Okay.
Our sources define it formally as the lowest division of a building, specifically designed to support and anchor the superstructure and transmit its loads directly to the earth. Its primary role is to ensure the entire building's weight is safely transferred without causing the ground itself to fail by punching through or compressing too much, or allowing the building to settle unevenly, which causes cracks and other problems.
So safe transfer of weight is job number one.
Absolutely. Within the foundation system, the footing is specifically defined as that part of the foundation bearing directly upon the supporting soil. It's essentially the widened base of a foundation wall or column designed specifically to spread the load over a larger area.
Wider base, less pressure on the soil.
Exactly. Think of snowshoes spreading your weight on snow. Same principle. Here's a step-by-step look at how foundation works and where the engineering genius truly comes in.
Okay, let's hear it.
1. First, the immense loads from the entire building. Its own dead weight, the live loads from people and furniture, wind pushing on it, everything, are collected by the structure and transmitted vertically down through the columns or foundation walls. These are concentrated forces.
Weight traveling downwards.
2. These concentrated loads then connect to a footing. The footing's primary job, as we said, is to take that concentrated force and spread it over a wide enough area of the supporting soil beneath it. This is absolutely critical to ensure that the bearing capacity of the soil, how much weight the soil can safely support per unit area, is not exceeded.
Don't overload the ground.
Precisely. If the load is too concentrated, the soil would compress too much, or shear, or simply fail, leading to significant settlement or even catastrophic collapse of the structure.
Okay.
3. Now, as the building's weight pushes down on the footing, Newton's third law kicks in. For every action, there's an equal and opposite reaction. The soil pushes back up against the underside of the footing.
The ground pushes back.
Yes. And this interaction creates complex internal forces within the footing itself. Primarily, it creates tension along the bottom face of the footing. The soil pushing up is trying to bend the footing upwards in the middle, stretching the bottom concrete. At the same time, there's compression on the top side.
Tension at the bottom, compression at the top.
Right. 4. This is precisely why most modern footings are made of reinforced concrete. Concrete is very strong in compression, but relatively weak in tension. So reinforced concrete footings have steel reinforcing bars, or rebar, strategically placed near the bottom surface.
The steel bars handle the stretching.
Exactly. Those rebar elements are specifically designed to effectively manage and resist that tension caused by the upward soil pressure, ensuring the footing maintains its integrity and prevents cracking or failure under these immense forces. It's a brilliant combination of materials.
Concrete for compression, steel for tension.
That's the magic of reinforced concrete. Beyond the deep foundation elements like footings and piles, there are also different types of substructures that define the space immediately below the ground floor, depending on the design.
What kinds are there?
The simplest is probably a slab-on-fill, sometimes called slab-on-grade. This is basically a concrete slab that rests directly on a prepared bed of compacted fill material directly on the ground. It's not suspended. Very common, often cost-effective for ground floors, especially in warmer climates.
This is a slab on the ground.
Pretty much. Then there's a crawl space. This is typically found in buildings without a full basement. It's an unfinished but usually accessible space between the ground and the underside of the first floor structure, usually less than a full story height.
Why have a crawl space?
Often used for utility access, running pipes and wiring, and it helps keep the main floor structure away from ground moisture, but it's not designed as living space.
Okay. Access and moisture control.
And finally, a basement. This is the lower story of a building, which is either partly or entirely below grade, ground level. Unlike a crawl space, basements are often designed as habitable living space, or used for storage, laundry rooms, mechanical equipment, etc. They require more extensive excavation and waterproofing.
It's full underground level.
Right. Each type, slab, crawl space, basement, serves different purposes based on factors like the site conditions, especially the water table, the local climate, the budget, and the desired functionality of the building.
Okay, we've talked about the planning, the process, the structure, the money, the tools, even the unseen forces at play. Now let's explore the fundamental building blocks themselves.
The actual stuff it's made of.
Exactly. The diverse and fascinating materials that turn designs into reality. This segment feels like it could get really detailed, showcasing the unique properties and applications of each, revealing the ingenious choices builders and designers make every day.
Absolutely. The choice of materials is absolutely central to construction. It influences everything from a project's cost, schedule, and durability to its aesthetics, its environmental impact, its fire resistance, its acoustic properties, everything.
Where should we start? Perhaps with the oldest.
Makes sense. Let's begin with wood. An ancient material that, remarkably, even after thousands of years of use, remains one of the most widely used building materials today, especially in residential construction in many parts of the world.
Still going strong?
Definitely. Wood is essentially the tough, fibrous, cellular substance that comes from trees. It's a renewable resource sourced from managed forests, processed at lumber yards, and easily accessible through suppliers like Home Depots. Its enduring appeal lies in its versatility, its relative ease of workability, its strength-to-weight ratio, and its natural aesthetic beauty.
People just like wood.
They do. Wood is generally classified into two main types, hardwood and softwood. And the names can be a bit misleading.
How so?
It's based on the tree's botanical classification, not necessarily its physical hardness. Hardwoods come from deciduous trees, those that lose their leaves, while softwoods come from coniferous trees, evergreens with needles.
Ah, okay. So what are the general property differences?
Generally, hardwood tends to be darker in color, heavier, and denser. It's typically more expensive than softwood. Its impressive durability means it can last for several decades, and many hardwoods boast natural resistance to decay and insects, as well as good weather resistance.
So strong and long-lasting.
Usually, yes. Because of these properties, hardwood is typically utilized for things like high-quality flooring, cabinetry, fine furniture, and sometimes structural elements where strength, longevity, and aesthetic appeal are paramount. Think oak, maple, cherry, walnut.
Okay, and softwood.
Softwood, by contrast, usually has a lighter color and weight, making it less expensive and often easier to work with. While it generally lasts for over a decade, especially when properly treated against decay and insects, it's not naturally as durable as most hardwoods.
So less durable, cheaper.
Typically, softwood is commonly used for structural framing, like wall studs, floor joists, roof rafters in houses, sheathing, window and door frames, and extensively in furniture production as well. Think pine, fir, spruce, cedar. It's the workhorse of residential framing.
The backbone of many houses.
Absolutely. Now, while wood offers immense versatility, it's a natural material, so it can have wood defects. These can occur due to issues during the tree's growth, like knots, or problems with cutting, stacking, or drying the lumber. Natural forces like wind can cause stresses, and biological impacts from insects or fungi are also a concern.
Things to watch out for.
Yes. For structural integrity, these defects must be minimized or accounted for in the grading and design process. Minor defects might just add visual character, but significant ones can compromise strength.
Grading is important then.
Very. Understanding wood terminology is also key. Timber usually refers to unprocessed wood, like logs or large squared-off sections, suitable for building material. Lumber is processed timber. It's been manufactured by sawing, resawing, planing, cross-cutting to standard sizes, and grading.
Timber is raw. Lumber is processed.
Good summary. Dressed lumber is lumber that's been surfaced with a planing machine to achieve a smooth finish and uniform size. You might see S2S, smooth on 2 sides, or S4S, smooth on 4 sides. Rough lumber is sawn, edged, and trimmed, but not surface smooth.
Dressed is smooth, rough is not.
Simple as that. And kiln-dried lumber is crucial. This is wood that has been seasoned or dried in a controlled environment, a kiln using specific conditions of heat, air circulation, and humidity. This reduces the moisture content significantly.
Why is that important?
Because it dramatically improves the wood's stability. It minimizes shrinking, warping, and twisting after the lumber is installed in a building as it reaches equilibrium with the surrounding air humidity. Using green, undried lumber is asking for trouble later on.
Got it. Dry wood is stable wood.
Pretty much. Next, let's move to masonry. This covers materials like brick, stone, and concrete block. Let's focus particularly on concrete, often called liquid stone because of its amazing transformative properties.
Liquid stone, I like that.
Concrete starts as a semi-liquid mass that can be cast, molded, or formed into virtually any shape. Then, through a chemical reaction with water called hydration, it hardens and becomes stone-like in strength, hardness, and durability. This hardening process itself is specifically called setting.
The transformation from liquid to solid.
Exactly. The composition is straightforward, but the proportions are vital. When cement is mixed with water and a fine aggregate like sand, typically less than 6 millimeters or 14-inch, it forms mortar, used to bond bricks or blocks, or cement plaster stucco, used as a finish coating.
Cement, water, sand, mortar or plaster.
Right. But when cement is mixed with water, fine aggregates, sand, and a large aggregate like gravel or crushed stone, typically more than 6 millimeter, it produces concrete.
Add gravel, get concrete.
That's the key difference. So the main components of concrete are cement, the critical binder. It's a finely ground powder material, usually a calcined mixture of clay and limestone, which, when combined with water, undergoes hydration and develops adhesive and cohesive properties, binding everything together as it hardens. Aggregates. These are inert granular materials like sand, fine aggregate, and gravel or crushed stone, coarse aggregate. They form the bulk of the concrete mass, providing volume and strength and reducing shrinkage. Water. This is essential for the chemical reaction hydration with the cement. It forms a paste that coats the aggregates and binds the entire mass together upon hardening.
Cement is the glue, aggregates are the bulk, water makes it react.
Excellent summary. Now, the cement-water ratio is incredibly important for concrete quality. It's often expressed in proportions, like a 1.2.3 mix might mean 1 part cement, 2 parts sand, 3 parts gravel by volume or weight, plus a specific amount of water.
The recipe.
Exactly. And the critical insight here, often counterintuitive, is the less water used in mixing, while still achieving workability, the better quality of concrete in terms of strength and durability. Too much water weakens the final product significantly.
Less water is stronger.
To a point, yes. But you need enough water for the chemical reaction and to make the mix workable, able to be placed and finished. So the mix should not be too dry nor too wet. It's a delicate balance that requires careful control, often specified by engineers.
Finding that sweet spot.
Precisely. Historically, it's interesting to note other cementing materials were used before modern Portland cement. Lime, made by calcining limestone, was used for millennia in mortars and plasters. Gypsum, the source of plaster, including plaster of Paris, is another binder.
Older types of cement.
And fascinatingly, pozzolan cement, first developed by the ancient Romans, was a mix of slaked lime with volcanic ash called pozzolana. This mixture had the remarkable property of hardening underwater, which revolutionized Roman construction and enabled structures like the Pantheon Dome and harbor works that still stand today.
Wow, Roman ingenuity.
Absolutely. Modern Portland cement, by the way, got its name because its inventor thought the hardened concrete resembled a high-quality building stone quarried in Portland, England.
Ah, okay. That makes sense.
Moving on to metal. It's truly the indispensable backbone of most large modern structures, enabling the soaring heights and expansive spans we see in contemporary architecture.
Steel frames, rebar, and concrete.
Exactly. Metals used in construction are broadly categorized into two main groups, ferrous and non-ferrous.
Iron-based and not iron-based.
Spot on. Ferrous metals are those in which iron is the principal element. Steel, in all its various forms, structural steel, stainless steel, reinforcing steel, is the dominant example.
Advantages ferrous metals.
Their main advantages include generally high strength, durability, stiffness, and often lower cost compared to non-ferrous alternatives for structural applications. Their magnetic properties are also useful in electrical appliances and motors. They offer strong durability, good ductility, ability to deform without breaking, and very high tensile strength, making them ideal for structural frames and rebar. Corrosion is a potential issue, but it can be managed effectively by adding alloying elements like chromium and stainless steel, applying protective coatings like galvanizing or paint, or using techniques like cathodic protection.
Strong but need protection from rust.
Generally, yes. Then you have non-ferrous metals. These are metals containing no iron or very little iron. Common examples in construction include aluminum, copper, lead, zinc, brass, and bronze.
What are their advantages?
Non-ferrous metals offer a different set of desirable properties. They often have attractive colors, like copper or brass. Many have low density, like aluminum, making them lightweight. They typically boast excellent electrical and thermal conductivity. Copper is prime for wiring, aluminum for heat sinks. They are generally easy to fabricate. They can be readily rolled, forged, welded, cast, and machined. And perhaps most importantly, many have high resistance to corrosion and weathering, making them excellent for roofing, copper, zinc, flashing, gutters, window frames, aluminum, and plumbing, copper.
Lighter, corrosion-resistant, good conductors.
That covers many key points. The distinct properties of each type, ferrous and non-ferrous, allow engineers and architects to choose the perfect metal for a vast range of construction applications, from the massive, load-bearing structural frames of skyscrapers using steel, to intricate decorative finishes, durable roofing systems, and highly functional building systems like plumbing and electrical wiring, often using non-ferrous metals. Material selection is key.
Using the right metal for the right job.
Exactly. Next, let's talk about plastics. This is a huge and diverse group of synthetic materials, typically derived from common substances like coal, salt, and oil through chemical processes. Plastics have gained immense traction in construction over the last few decades due to a surprising array of advantageous qualities.
Plastics in building, like pipes.
Pipes are a big one. PVC, PEEK, but there's much more. Their properties make them surprisingly versatile. First, they are exceptionally lightweight and strong. Plastics generally have a high strength-to-weight ratio, which greatly facilitates transportation, loading, unloading, and installation on site. This can reduce labor costs and the need for heavy lifting equipment compared to traditional materials. Second, they are highly corrosion-resistant. Unlike metals, plastics don't rust. They have strong weather-fighting ability, which leads to less maintenance over a building's lifespan. Some specialized plastics, like PPS, polyphenylene sulfide, are even used for applications exposed to highly corrosive chemicals at high temperatures. Great for pipes, window frames, siding, roofing membranes. Third, they can provide impermeable surfaces with tight seals. Plastics are made from long polymeric chains, which makes them inherently water repellent. This property, combined with the ability to form tight joints and seals, helps buildings be leak-proof, crucial for roofing, weather barriers, and flashing. Fourth, many plastics can be engineered to be fire-resistant. While plastics are organic materials, special additives, like antimony trioxide mixed with brominated compounds, can be incorporated during processing to significantly slow down the combustion process and reduce flame spread, enhancing building safety. Fire ratings are important here. Fifth,
Plastic is remarkably flexible with anti-vibration properties. Some plastics can undergo large deflections, bend significantly without permanent deformation. This flexibility can be advantageous, for instance, during earthquakes, potentially improving a building's seismic performance. Their inherent properties also help dampen airborne noises, contributing to better acoustics. Finally, plastic acts as an excellent thermal insulation product. This is often achieved by foaming the plastic, incorporating tiny gas bubbles, creating materials like expanded polystyrene, EPS, or extruded polystyrene XPS boards, or polyurethane spray foam. These lightweight materials offer very high thermal resistance, significantly improving a building's energy efficiency and reducing heating and cooling costs when incorporated into walls, roofs, and foundations.
Wow, that's a lot more versatile than I realized. Lightweight, durable, insulating.
They offer a unique combination of properties that solves many modern construction challenges. Our last major category of materials today are building boards.
Building boards, like sheets of material.
Exactly. These are generally defined as sheets of building materials often faced with paper or vinyl, suitable for use as a finished surface on walls, ceilings, etc. They are essentially engineered panel products designed for specific performance requirements, often allowing for faster construction and tailored interior or exterior finishes. There's a huge variety.
Okay, give us some examples.
Let's run through some common types. Plywood is a classic. It's made by bonding together thin layers of wood veneer. Crucially, the grain direction of each layer, or ply, is oriented at right angles to the adjacent layer. This cross-graining is what gives plywood its strength, stiffness, and resistance to warping and splitting. Very versatile structural sheathing and underlayment. Insulating fiberboard, sometimes called softboard. This is typically made from wood fibers, sugarcane fibers, bagasse, or sometimes asbestos fibers, though asbestos is now heavily restricted due to health risks, mixed with a binder and formed into boards, often used for acoustic insulation or as a sheathing with some insulating value. Chipboard particle board. This is a large class of boards made from wood particles, chips, shavings, sawdust bonded together with a synthetic resin or binder under heat and pressure. It's often faced with a wood veneer or melamine for furniture or shelving. Particle board usually refers to boards made from relatively small particles, generally less strong and less moisture resistant than plywood. Gypsum board, universally known as drywall or plasterboard. This is a ubiquitous interior wall and ceiling finish. It consists of a hardened core of gypsum plaster sandwiched between sheets of heavy paper or fiberglass mat. It's valued for its fire resistance, smooth finish, ease of installation, and relatively low cost. Straw board. An interesting one, a hard board made of compressed wheat straw, processed at high temperatures and typically covered with tough craft paper. Sometimes used as an eco-friendly building panel. Asbestos cement board. Historically used, but again, asbestos raises major health concerns now. It was a dense, rigid board with a high proportion of asbestos fibers bonded with Portland cement. It was very resistant to fire, flame, and weathering, but ironically had low resistance to heat flow, poor insulation. Mostly phased out. Cork board. Made from cork granules from the bark of the cork oak tree, mixed with a synthetic resin, compressed, formed into sheets, and baked under pressure into rigid boards. Excellent for thermal and acoustic insulation and used for tack boards. Sustainable material. Paperboard, basically thick, stiff sheets made from paper pulp pressed into boards of varying thicknesses. Used more in packaging, but sometimes in building for specific layers or templates. Mineral fiber board. These are typically thick mats of mineral fibers, usually glass wool or rock wool, often covered with a stiff paper or foil backing, forming semi-rigid or rigid boards used primarily for thermal and acoustic insulation. Plastic foam boards. We touched on these with plastics. Polystyrene, EPS and XPS, and polyurethane, polyisoplastics, are formed to expand significantly during manufacturing, an example 40 times original volume, trapping gas bubbles. These rigid foam boards are extremely lightweight and provide excellent thermal insulation, widely used for insulating walls, roofs, and foundations to improve energy efficiency.
Plywood, drywall, particle board, foam boards. Quite a range of sheet materials. It's truly incredible to see the ingenuity behind these engineered materials.
It really is.
From the ancient reliability of wood and stone to the modern advancements in concrete, metals, plastics, and composites like these boards, the builder's arsenal is constantly evolving. Each material is carefully selected or engineered to meet specific performance requirements, strength, insulation, fire resistance, cost, aesthetics, and contribute to the overall success of a building. Material science is at the heart of modern construction. #TagOutro. What an incredible journey we've taken through the world of construction today. Seriously, deep dive.
We covered a lot of ground.
We really did. from understanding its fundamental definitions and the intricate sequential nature of a project timeline,
All those steps.
to deconstructing the complex layers of a construction budget, hard costs, soft costs, contingencies,
Following the money.
mastering the specialized language in the build, all those terms like RFIs and change orders,
Speaking the lingo.
and then exploring the vast arsenal of tools, from hand tools to heavy equipment, and the very anatomy of a building itself, from foundation to superstructure.
Plus the materials. Wood, concrete, steel, plastics, boards.
Exactly. And we even took that fascinating detour into the rich tapestry of Filipino vernacular construction terms, seeing how culture and language can shape practice in unique ways.
That was a great addition.
This deep dive, we hope, has offered you, the listener, a comprehensive yet digestible pathway to becoming truly well-informed about the built environment that surrounds us every single day. Hopefully you see buildings a little differently now.
Indeed. As you go about your daily life, I really encourage you to look at the buildings around you with new eyes. Try to appreciate the incredible thought, the meticulous planning, the coordination, and the diverse materials and skilled labor that go into their creation.
It's easy to take them for granted.
It is, and consider this as a final thought. The relentless evolution of construction methods and materials is not stopping. It's being constantly driven by new, pressing challenges like climate change, the urgent imperative for sustainability, energy efficiency, resource depletion, and the demands of rapid global urbanization.
Big challenges ahead.
Huge challenges. These forces will continue to transform our skylines and our living spaces in ways we can probably only begin to imagine today. The next few decades will undoubtedly see truly revolutionary approaches to how and with what we build. It's an exciting and critical time for the industry.
Absolutely. The world of construction is never static. It's a living, breathing testament to human ingenuity, constantly adapting.
Never a dull moment.
Thank you so much for joining us on this deep dive into the fascinating world of building.
It was a pleasure. We hope you continue your own exploration of the incredible, complex, and essential world around you.